Hello class, in this lecture I will talk about ANOVA table. We'll be doing a problem from Hawk's Learning, how to solve this problem. So this is how your ANOVA table looks. This is the source of variation, the first column. So this is the first one is between treatments, groups, factors, or they can say sample mean versus grand mean. And the this column is error within groups, treatment, factors, individual versus respective means. The respective mean is what you will be doing, and this is total individuals versus grand mean, that is what. And the second column is sum of squares. This is sum of the squares of treatment, and this is sum of the squares of error, and then we have sum of the squares of total or total sum of the squares. So that is represented by those terms. So okay, so here I kind of tried to explain. If you see, sum of the squares of total plus sum of the squares of error is going to give you sum of the, okay, so this is sum of the squares of treatment plus sum of the squares of error is going to give you sum of the squares of total. So the next one is degree of freedom. The degree of freedom for treatments, between treatments, would be k minus 1. So if you have uh, like 3 treatments, then you will have degree of freedom 2. So here k represents, so this k is the number of treatments, and then this n minus k, n represents the number of samples, and then that's for error degree of freedom, and n minus k, n minus 1 is the degree of freedom for the total. So if you see again this one, when you do k minus 1, so this k minus 1 plus n minus k is going to give you n minus 1, and then MST is, so if you divide this SST, so if you divide this divided by this, so I put divide here, is going to give you MST, and then SSC divided by n minus k is going to be MSC. And then if you divide this and this, you'll get F value. So that is how you are going to solve these problems. So I will try to use an example from Hawk's Learning and try to solve these problems and see if we can solve them. So here is, consider the table, and they are asking you to calculate this one, which is the sum of the squares of experimental error. So this is, they're asking you to, so obviously you know this plus this is going to give you this. So let me type in this value. I will copy this value and paste it in our Word document. So this will be the this value, and then this value would be this. So obviously this plus this is going to give 4985, and they are asking us to calculate what is here. So what is, let me go here, what is this? So obviously this one, let me highlight it, uh, plus whatever is here in the second cell in the question mark should be equal to 8449. So the question mark here, would be, the value would be 8449.04 minus 4985.6. So that is let me calculate that and see what is the value of it. So 8449.04 minus 4985.6. So this would be 3463.44. So that means this value is 3463.44. So that's how you'll be calculating. So let me type in that value, 3463.44 is our value. So I suggest you to fill the entire table because they will be again asking you some questions related to it. So what is the degree of freedom among treatments? So they are asking you what is this. So they gave you this as, let me see. So they gave you this. This is given as let me copy that. So this is 17. So this value is 17. How about this? They gave us this also. So let me see what is that. So they gave us this. So you see, if I would have had one number here, I could have subtracted that from 17, but now they gave me this and then this is question mark, and I have this. So our equation of MST is this divided by this, k minus 1. So the question mark, so I will do, so SST divided by this k minus 1 is going to give me MST. So SST in this formula is 4985.6 divided by k minus 1 is going to give me 997.12. So I have to determine what is this k minus 1, so I can divide this, take this here and take k minus 1 that side. So k minus 1 would be 4985.6 divided by 997.2. So this is going to be, let me check, 4985.6 divided by 997.12 is 5. So this value here is 5. So if this is 5, k is 6. That means you have 6 treatments or 6 groups or 6 populations in which you are comparing. So that is good. So I will put that as k. So here this value would be 5. So I will put 5 in this. So that would be good. And then degree of freedom of experimental error. So this is going to give me if this is 17 and I know this is 5, this should be 17 minus 5, which is 12. So this is here is 12. So I will do 12 and then calculate the mean square experimental error. So what is they are asking us, what is this? So this is, you can do this divided by this, so that is 3463.44 divided by 12. So what is that? 3463.44 divided by 12. So that is 288.62. So this is going to be 288.62. So that's how you will be solving these problems. And then they gave you f value, so the f value is 3.45. So let's 288.62 is what we have to enter here. 288.62. Okay, so how about now? So what is the sum of the squares of sample means about the grand mean? So they are asking you the sum of the squares is this, sample means about the grand mean. So this is sample mean versus grand mean, you see, and the sum of the squares would be this value. So whatever value is in the first column, that is what it is. So this is what would be the sum of the squares of sample mean about the grand mean. So I will do this, and then what is the variation of, when they say variation, it is sum of the squares of the individual measurements about their respective means. So if you go to our sheet, it says individual versus respective mean. So that means whatever value you have here, that will be the value 3463.44. So you will do 3463.44 would be our individual measurements about their respective mean. So this is all the terms will be same, it's just you have to select the which one they are asking you. What is f at 0.05 level? So this is the critical value of f at 0.05. So as I discussed previously in this lecture, the critical value would be, the formula would be f alpha degree of freedom 1 and degree of freedom 2, and then they gave us f at 0.05. That is what question is asking you. So if you look at 0.05, alpha is 0.05. So this means alpha is 0.0. So degree of freedom 1 will come from here, which is 5. So I will use a different color. 5. So this would be 5, and then degree of freedom 2 will be for the second column, which is 12. So you will look for f.055, 12. So that is what we have to look for. So you can go to our course and then go to modules, and then module 0, go to calculation aids, and then go to statistical tables, do enable editing. Currently I am in Poisson distribution table. I'm looking for f.05, so I will go to f table and go to 0.05, and our degree of freedom is 5, 12. So degree of freedom 1 is this way. So this is degree of freedom 1, and degree of freedom 2 is this way. So I am looking for degree of freedom 1 is 5, and degree of freedom 2 is let me go and check, is 12. So I will go and check, do degree of freedom 12. So that is going to give me 3.1059. So I will enter that. That is my critical value. So my critical value would be 3.1059. 3.1059. So I will submit it, and then is f significant at 0.05. So if so we discussed this concept. If let me go to a new sheet, I will insert a new blank sheet. So if I have f greater than f alpha, degree of freedom 1, degree of freedom 2, we reject our null hypothesis. The other way of saying is it is significant. So is it significant? You will say yes it is. So yes, it is significant. So when we reject null hypothesis, that means it is significant. So our f value, if you see, let me check what would be our f value. Okay, so our f value is 3.45, and our critical value, which we looked at in this table, was 3.1059. So this is 3.1059. So is this statement true? This is a true statement. That means yes, it is significant. Suppose if this value would have been something like 3 greater than, so this is, I'm supposing it, greater than 3.109. Now this is a false statement. 3 is not greater than 3.1059. So this is a false statement. Then you will say it is not significant. So I go here, currently it is significant because this is greater than, f is greater than 3.45 is greater than 3.1059. So you are saying yes, it is significant, and you submitted. So that is how you will be solving problems in Hawk's learning. So we will try to, so this you can do again. Let's see if you can do this kind of problems. So this is when data is given, how do you solve a problem. So in this again we will be discussing hypothesis testing. So I will open up a new page. Okay, so the first thing is when the data is given like this, they say a study compared 3 different display panels for use by air controllers. Each display panel was tested in a simulated emergency condition. 12 highly trained air traffic controllers took part in the study. 4 controllers were randomly designed to each display panel. The time needed to stabilize the emergency condition was recorded. The results of the study are given in the following table. Let mu A, mu B, mu C represents the mean times to stabilize the emergency condition when using display panels A, B and C respectively. The faster the resolution of the better. So the faster the resolution, the better it is. So we have a data set, that means faster means lower values. So given the following, conduct analysis of variance and answer the following questions. So the first thing is you draw a box plot. So this is shown. So what is your null hypothesis? So when you are comparing 3 samples, so the question says you have mu A, mu B, mu C. So you have 3 treatments. So the treatments K is 3. This is treatment. A, B, C is treatment. So your null hypothesis should be mu A is equal to mu B is equal to mu C. So that is when you do hypothesis testing. Your alternative will be mu A. Your alternative would be at least one is different. So if one of them have different resolution value, then it is alternative is true. So they asked us what is the null hypothesis, that is mu A is equal to mu B is equal to mu C. So you will do that, and then next the problem is referring to the so this is again the same question, referring to the box plot, which height seems to have higher mean. So if clearly you can see C has a higher mean, so I will do panel C, and then referring to the referring to the box plot for air controls, the variation between panels generally seems to be. So the variation looks, usually even though you have the variations, this has a little bit more variation. The assumption which we made while doing these ANOVA problems is the variations are equal. So that means sigma 1 square is equal to sigma 2 square, or you in this case sigma a square is equal to sigma b square, sigma c square. So that is the assumption on which your ANOVA is working. So you can just say, even though they look different, you can just say they are kind of equal. And then referring to the ANOVA table, the common standard deviation is, now the idea is you have to get the ANOVA table from these values. So I will copy this data. I will go to our calculation aids. This is chapter 12 calculation aids. So I have this and then I will copy the data somewhere here first, and then so treatment A I will do, take it here, treatment B I will take it to treatment 2, and then C I will take it here. So the other thing they are asking us, so if alpha is not given, you just assume alpha is 0.05. So you'll assume this alpha is 0.05. So you'll get this ANOVA table. So this is the ANOVA table. If you see, this would be your ANOVA table. So I might highlight it with a different color, maybe. I'll use a light color. Yeah. So that is your ANOVA table. So now they are asking you what is the common standard deviation. So we discussed in our previous lecture that this is this 8.30, that is common variance. This is common variance. So to calculate common standard deviation, you do square root of common variance, square root of common variance. So I can do somewhere here, I will do, so this is common standard deviation I am calculating. So this is equal to square root of whatever value is here. So that is 2 point, so let me unhighlight this maybe. No, I will do no fill here. So that is 2.88193. So I will copy that and paste it here. So I'll submit that. And then they are asking you give the degrees of freedom for treatment. So the degrees, if you go here, among treatment, the degrees of freedom is this value. I will just highlight that cell by some other color, maybe yellow would be good. 2, the degree of freedom for treatment, if you say this is treatment. So this is 2, so I will type in 2, and then the sum of the squares of error. So sum of the squares of error, so the SS represents sum of the squares and this is error. So the sum of the squares of error would be this cell, because this is the error. So 74.75 would be our answer. So I will type in that and do, and then refer to the test statistic is. So referring to the one way ANOVA, the test statistic is. So I will go to this again. The test statistic value here, if you see, is 30.11. So that would be our test statistic value. And then what is the critical value? So the critical value, if you go and see, this is our critical value, 4.256. So I will do this and calculate the put that value there, and then finally the p-value. So again, the p-value, usually p-value, it is here. So the p-value is this. Again I will highlight it and then copy that and paste it. So that is the p-value. So based on what do you conclude, right? So we said if this one way is test statistic value, you compare with this and say, or how does what's happening, right? So the test statistic value, which is f value greater than f alpha degree of freedom 1 degree of freedom 2. So this is the critical value. So that is 4.25, and your test statistic value is this. This is your test statistic value. So this would be 30.11. So if f 30.11 greater than 4.25, so this is a true statement. So we reject our null hypothesis. We reject our null hypothesis. That means at least one is different. So at least one is different. So if you see, our null hypothesis was what was our null hypothesis? Our null is mu a is equal to mu b is equal to mu c. Alternative is, so if we reject this, that means this is true. So now which is better? So they're asking us which panel is better based on the hypothesis. So you can look at this, and we are looking for lowest resolution, so panel B should be better. So I can say panel B is a better choice. So that is how you will be solving these kind of problems. So this concludes my lecture on ANOVA. Thank you.